This is a recast of the 7,700-word piece Evidence Lower Bound, ELBO, from gupt5.blog. This article is about Evidence Lower Bound, ELBO, a tool used in Bayesian inference to estimate the marginal probability of a model. Let's listen in.
So today we'll be talking about the evidence lower bound, or ELBO. ELBO is calculated by the process of evidence optimization, where an approximation distribution is selected from a family of distributions that are flexible enough to represent complex data structures.
Right, and this provides a lower bound for the true log evidence, which can be accurately calculated for complex non-analytical models. It does come with some restrictions, though, like depending on the family of distributions chosen and the possibility that it won't converge to the global optimum.
Exactly. Nevertheless, ELBO is a powerful tool for Bayesian inference that enables practitioners to conduct statistical inference on complex models.
Now, ELBO plays a crucial role in machine learning by providing a lower bound for the marginal probability of a dataset, which is a key concept in Bayesian inference. By maximizing the ELBO, we can optimize the parameters of a generative model to fit our data in a probabilistic way.
That's right. This approach allows us to process complex and high-dimensional datasets and to quantify the uncertainty of our predictions. What's more, ELBO has become a cornerstone of modern deep learning by enabling more flexible models and better interpretability of their internal workings.
So what are some approaches to optimizing ELBO?
Well, one frequently used approach is known as stochastic gradient descent, SGD. SGD is an iterative optimization algorithm that updates the model parameters in small batches rather than all at once. By using a small batch size, SGD can process datasets that are too large to fit into memory and speed up the training process.
I see. But since SGD only goes in the direction of the negative gradient, it may not find the optimal solution, right?
That's right, but this can be solved by using more sophisticated optimization methods like ATOM or ATOGRAD.
So to summarize, ELBO is a tool used in Bayesian inference to estimate the marginal probability of a model. It's calculated by maximizing a lower bound on the marginal probability derived from the posterior distribution. This allows us to select a model with the best probability rating while also considering model complexity. ELBO has increasingly gained significance in machine learning, where it's used in variational inference procedures to estimate posterior distributions.
That's right. ELBO is typically split into two separate components, one for the data distribution and one for the approximate posterior distribution. The data distribution component is basically the expectation of log likelihood under the given model, while the approximate posterior component is the negative KL divergence between the true posterior and the chosen approximation.
And finally, we described the mathematical representation of ELBO. Given a dataset of independent and identically distributed, i.e. the observations X, we have a probabilistic model PAXes, whereas is the latent variable we wish to learn the true posterior distribution PAS X from the dataset. ELBO can then be represented as a function of both model parameters and approximate posterior KIS X parameters.
ELBO has various practical applications in machine learning, such as in recommendation systems, natural language processing, and image recognition. In a recommendation system, ELBO is used for inferring user preferences and predicting product recommendations.
In natural language processing, it helps to improve language models by enabling efficient training on large datasets. For image recognition, ELBO is used to learn underlying representations of images and use them for tasks like object recognition and classification.
The rise of AI has led to incredible advancements in image and speech recognition. These technologies are being used in a variety of applications, such as facial recognition for security purposes and speech-to-text software for accessibility. Convolutional neural networks and recurrent neural networks are two popular approaches to image and speech recognition.
But there are still limitations with these technologies, and further research is needed to enhance their accuracy and efficiency. The widespread use of recommendation systems, especially in the context of recommendation engines for e-commerce, has dramatically increased the demand for estimating scalar parameters for massive datasets.
Rating estimation algorithms, which are often adopted by recommendation systems, often use a combination of matrix factorization and regularization techniques, including Tikhonov regularization. But using such techniques can lead to challenges in terms of the practicality of processing high-dimensional datasets.
Natural language processing, NLP, is a subfield of AI that focuses on the interaction between computers and human languages. NLP algorithms analyze and understand humans' natural language, including speech and text, to extract meaning and intent. These algorithms can be used for a variety of applications, including chatbots, machine translation, sentiment analysis, and more.
ELBO has proven to be a practical method for training NLP models and improving their performance on various tasks. Finance is one of the major fields that can greatly benefit from the use of the evidence lower bound ELBO method. This technique can help with financial modeling and analysis by providing more accurate estimates of decision probabilities and outcomes.
Additionally, ELBO can be used to improve portfolio management strategies by maximizing expected returns while minimizing risk at the same time. Overall, incorporating the ELBO approach into financial decision-making can lead to better informed and successful investment decisions.
To sum up, ELBO is a powerful tool that helps with model selection and performance optimization in many machine learning applications. By maximizing ELBO, practitioners can ensure their models effectively capture important features of the data while avoiding overfitting. Although ELBO can be difficult to calculate in some cases, there are several approximation techniques that can be used for efficient estimation.
While ELBO is a powerful tool for estimating models with hidden variables, it also brings some challenges. One of the biggest challenges is computational complexity, particularly requiring computation of expectations under complex distributions, which can be difficult and time-consuming.
Furthermore, ELBO may not always provide the most accurate estimates of model parameters, especially in cases where there is significant model specification or if there are multiple local optima. These challenges underscore the need for further research and development of techniques to overcome the limitations of ELBO. Another limitation of ELBO is that it fundamentally relies on the quality and quantity of data available for inference. Specifically, ELBO requires a sufficient amount of data to estimate model parameters with adequate accuracy. Limited or poor data quality can lead to inaccurate or biased parameter estimates, which ultimately affects the validity of inferences based on ELBO.
Therefore, caution should be taken when using ELBO in situations where limited data availability is an issue. Additionally, there is a trade-off between model flexibility and complexity when using ELBO. While a more complex model may potentially capture more complex relationships within the data, it may also lead to overfitting. It is therefore critical to carefully align model complexity with the amount of available data, as increasing complexity beyond what the data can support may not lead to more accurate predictions, but instead impair model performance.
Another point to consider is the initial parameterization of the ELBO. Poor initializations can lead to suboptimal solutions as well as a slower convergence rate. Thus, practitioners should take care to use appropriate initialization strategies, such as random or heuristic methods, when dealing with more complex models.
Finally, ELBO can be compared to other optimization techniques such as Markov chain Monte Carlo, MCMC, and maximum likelihood estimation, MLE, while MCMC requires a large number of samples to estimate the posterior distribution, ELBO only requires a few. On the other hand, MLE requires a well-defined likelihood function, while ELBO can be used for models without well-defined likelihoods. However, ELBO can sometimes lead to an overestimation of the variational parameters, which is a disadvantage.
All things considered, ELBO and variational inference are powerful tools used in the Bayesian statistics and probabilistic modeling. By maximizing the evidence lower bound, we can obtain a lower bound for the unwieldy likelihood term in the evidence. This allows us to perform inference on the latent variables of the model and obtain the posterior distribution.
In the context of variational inference, ELBO offers an efficient optimization goal for approximating the true posterior. In the future, research could explore ways of incorporating domain-specific constraints into the ELBO optimization process. Another focus could be on developing new optimization techniques that are capable of tackling challenges posed by high-dimensional data. Furthermore, it would be interesting to investigate the potential applications of ELBO in reinforcement learning environments.
ELBO can be used to improve the performance of deep learning algorithms and architectures. Because ELBO offers a better measure of uncertainty, it can be used to reduce overfitting in deep learning models. Additionally, ELBO can provide an efficient optimization objective for finding the best model among a set of models and thus enable model selection.
Finally, ELBO can be applied to unsupervised learning tasks. Unsupervised learning involves learning the structure of data without labels, and ELBO provides a powerful tool for approximating intractable distributions through variational inference. This has resulted in significant progress in probabilistic modeling, which allows researchers to better understand complex data distributions and make more accurate predictions.